Hi, my name is Dr. Robin, and today I'm going to be explaining how to draw an electron configuration diagram for an atom. Before we jump in, we need to learn a few principles, all of which go back to what we talked about in the previous video in regards to electromagnetic forces. The first principle is based on an attractive electromagnetic force in which the lowest energy state is to be as close to the nucleus as possible. In other words, the negatively charged electron is going to be pulled towards the positively charged nucleus. And if you want to pull it away from the nucleus, you will have to apply force, or in other words, put energy in. The Aufbau principle is based on the fact that the lowest energy state is for the electron to be near the nucleus. Aufbau is German for build up, and that's what we're going to do as we place electrons in an electron configuration diagram. We will always put them in the lowest available energy level. The next two principles are based on repulsive electromagnetic forces. Remember, in the last video, we talked about the fact that electrons that are too close together will repel each other because they both have negative charges. You can push them closer together, but again, that will require an input of energy. Any electrons that are close together will be in a high energy state. So now let's look at our next two principles. Hund's rule tells us to spread electrons out as much as possible within a set of degenerate orbitals. What are degenerate orbitals? Basically, these are orbitals that have the same energy level. We'll come back to that in a bit. But first, let's talk about spreading electrons out. I want you to think about getting on a bus with a bunch of people, like say if your class is going on a field trip. If you think about how people distribute themselves throughout a bus where seats come in sets of two, people tend to choose a seat where they aren't sitting next to someone. So the first person will sit down, and then the next person will sit in a different row, and so will the next one, until all of the rows have one person in them. Only then will people start doubling up. I've even seen really good friends choose to sit in different rows. Often they'll be across the aisle from each other, or maybe one sitting in the row directly behind each other, so they can still talk, but they choose different rows because they want their space. Electrons are going to be the same way. If you have a bunch of different spots that are all more or less the same, the electron is going to go in a spot where it's not going to experience repulsive forces. Now again, this assumes that all of the orbitals are degenerate. In other words, they're at the same energy level. Maybe a better model than a bus would be filling up an airplane. If people could choose any seats they wanted without paying money, they would probably pick the first class seats, each person in their own row first, then doubling up in a row. Then people would pick the premium economy seats, and then last the regular economy. No one would pick the economy seat if they could get a first class seat. So you could think of degenerate orbitals as being a set of orbitals that is all the same type of seat. Or in other words, they're all at the same energy level. The final principle is the Pauli exclusion principle, which states that no two electrons in the same atom can have identical values for all four of their quantum numbers. Now, if you don't know what quantum numbers are, stop here and watch this video first. But as a general rule, the four quantum numbers basically provide an address that tells you where an electron is located. So basically, what this principle says is that no two electrons can exist in the same space under the same set of conditions. Each orbital will end up having two electrons, but that's because each of those two electrons will have a different value of the spin quantum number, m sub s. So now that I've clarified the rules, let's go ahead and look at an electron configuration diagram. This one doesn't have some of the higher energy levels like the 4f orbital, but we'll talk about those higher energy levels in a subsequent video. So what you see here is a representation of these orbitals based on their energy. The lower the energy of an orbital is, the lower on the screen it will appear. And I put our three principles off to the left for reference. Now, the only real part of the Pauli exclusion principle you're going to need to know for filling in these diagrams is that you can fit 2 electrons per orbital. Let's look at a very simple atom, lithium, and use it as an example to show you how these rules work. Lithium has 3 protons, so a neutral lithium atom would also have 3 electrons. So we're going to put 3 electrons in this diagram. Now, the Aufbau principle tells us that electrons are going to be put in the lowest available energy level. Remember, that's going to be the energy level closest to the bottom of the diagram, which in this case is the 1s orbital. So we start out by putting 1 electron in the 1s orbital. I've drawn it here with an upspin, in other words, an m sub s value of plus 1/2, but you could just as easily draw it with a downspin. The next electron is going to go in the lowest available energy level, and again, that is going to be the 1s orbital. We can't put another electron with an up spin in there because that would violate the Pauli exclusion principle, but we could put an electron with a down spin. Our third electron can't go in the 1s orbital. Yes, the 1s has the lowest energy of all the orbitals, but it's currently completely full, and therefore it's not available. So at this point, the lowest available energy level is going to be the 2s orbital. So again, I'm drawing in an electron with an up spin, but this could just as easily be a down spin electron. So now we've placed all 3 electrons, and now we're done with our electron configuration diagram for lithium. Let's try another electron configuration, this time for fluorine. Fluorine is element 9, so it has 9 protons, and a neutral fluorine atom would therefore have 9 electrons. Once again, we're going to start out putting electrons in the 1s orbital because that is the lowest available energy level. And again, we can put in 2 electrons so long as they have different spin values. So having placed 2 electrons, we have 7 electrons left to place. Next, we're going to place electrons in the 2s energy level. This time, we have enough electrons to fill the 2s energy level. So now we've used 4 electrons and have 5 left. So now 1s and 2s are full, and so the lowest available energy level for our 5 remaining electrons is going to be 2p. And this is where we start using Hund's rule because this is the lowest energy level at which we have degenerate orbitals. As you can see, we have 3 orbitals at the 2p level, and all of them have the same exact energy. So we're going to fill them up first by putting 1 electron in each. Now the thing I didn't mention about Hund's rule is that electrons have the lowest energy if all of them have the same spin. So I've made these all up spin electrons, but of course you could make them all down spin if you wanted. Now that used up 3 of our 5 remaining electrons, so we have 2 left. We now start to double up the electrons in our 2p orbitals, and now you can see the final result. We have 2 electrons in our 1s orbital, 2 in the 2s, and 5 in the 2p. Before we do another example, I want to talk a bit about magnetism in elements. Remember that when we talked about spin, I mentioned that electrons with 1 spin are pulled towards the north pole of a magnetic field, while electrons with an opposite spin would be pulled towards the south pole. Now I want you to imagine what would happen if you had an atom with only 1 electron. In this case, the electron would be pulled towards the north pole of the magnet, which means that the atom in general would be attracted to the north pole. But what if the atom had 2 electrons with opposite spins? 1 electron would be pulled towards the north pole, and the other would be pulled towards the south pole, and those forces would counteract each other. So from the atom's point of view, there would be no net attraction. So when we're trying to figure out whether or not an element would be magnetic, we can look at the electron configuration diagram to find out. If an atom has all of its electrons paired up within the orbitals, we call that diamagnetic. Dia means 2, so basically that means everything comes in 2. And because they're paired up, the atom will not be attracted to one magnetic pole or another. There will be no magnetic attraction. But if there's at least 1 unpaired electron, we call that paramagnetic. And it means that there will be a force pulling the atom towards one of the magnetic poles. And so we will observe magnetic attraction in that atom. Now that I've explained that, let's look at the electron configuration of iron. Iron is element 26, so it has 26 protons, and therefore a neutral atom of iron will have 26 electrons. So again, we start with a 1s orbital and place 2 electrons. Then we put 2 electrons in the 2s, which means we've used 4 electrons so far. Next, we add 6 electrons to the 2p, which brings us to a total of 10 electrons. The next lowest energy level will be the 3s orbital. We can put 2 electrons in there. And then we can put 6 more in the 3p orbitals. So now we've used up 18 electrons and we have 8 left. Now, if you look at the electron configuration diagram, you'll see that the 4s orbital is actually slightly lower in energy than the 3d orbitals. And so we're going to fill 4s next. And now we have 6 electrons left, and all of those should fit in the 3d orbitals. Again, we follow Hund's rule and we put 1 electron in each of the 5 3d orbitals, all with same spin, and then the remaining electron gets to double up. So, based on this electron configuration diagram, is iron magnetic? Well, all of the completely full orbitals are going to contain only paired electrons, so we usually look just at that last energy level that was filled, which in this case is the 3d. And here you see we have 1 3d orbital that contains paired electrons, but we have 4 3d orbitals with unpaired electrons. So that tells us that iron is paramagnetic and will be attracted to a magnet. that shouldn't come as a surprise to anyone who's ever played with magnets. So electron configuration diagrams are great tools for figuring out where electrons belong within an atom. As you can see, these really help in figuring out whether or not an element is magnetic or not, but they're also useful for other things in advanced chemistry topics. We will see more electron configuration diagrams in the future, including in the next video. I hope this was helpful, and I look forward to seeing you again soon.